Good day, students. Welcome to part two on the sum and difference identities examples. We're going to be going over an example today. We're going to be approaching it using two different methods. All right, so let's go ahead and write down the instructions for this example. So the task is to find the exact value, find the exact value of the given tangent expression in two different ways. All right, we're going to do it in two different ways. All right, so the expression under consideration in this example is tan 75 degrees. Okay? All right, so let's get our unit circles out. The question is 75 degrees on the unit circle, is it a common angle? If you look between 60 and 90, there's an angle there, so 75 degrees is not um, a common angle. But can we express 75 degrees using the sum or difference of two common angles? We absolutely can. How about we use one of the combinations that is possible is 45 and 30 degrees. Okay, so we're going to write tan 75 degrees as tan 45, the tan of 45 degrees plus 30 degrees. Okay, so what does this mean? This means that alpha, the first angle, is going to be 45 degrees and beta is going to be 30 degrees. All right? Okay, if you notice, we have the sum of angles here. Okay? All right. In this problem, we're going to be doing this, evaluating this trig expression using two methods. So let's go ahead and take a look at method number one. Okay? Method number one involves the use of the quotient identities for tan. So for this method, we're going to be using the formula tan alpha plus beta equals sine of alpha plus beta divided by cosine of alpha plus beta. Okay? Because we know using our quotient identities that tan of an angle theta is sine theta over cosine theta. So we're just using this, extending this to this problem. All right? Now, if we apply the sum identities for sine to the numerator, we'll have sine alpha cosine beta. Remember, for sine, the trig functions are different, but the sign stays the same, so we'll have a plus cosine alpha sine beta. That's for the numerator. And then for the denominator, we're going to apply the sum identities for cosine. So that's going to be cosine alpha cosine beta. So you notice the trig functions are the same, so the sign is going to switch, minus sine alpha sine beta. Okay? All right. So all we need to do is find out what alpha and beta, what the coordinate values are. Then we'll use the unit circle ratios to evaluate each expression independently. All right, so alpha, what is alpha? As indicated earlier, alpha is 45 degrees. So where's 45 degrees on my unit circles? Right here. So it's going to be roots 2 over 2 and roots 2 over 2. Okay? For my coordinates for 45 degrees. Now for beta, beta is 30 degrees. So the coordinates for beta is going to be roots 3 over 2. Looking at your unit circle here, and 1/2. Okay? Now if you look at your unit circle ratios, you note that the x-coordinate is your cosine. So these two represent the cosine. This is cosine 45, this is cosine 30. And the y-coordinate represents the sine. This is sine 45, and this is sine 30. Okay? All right, let's keep that in mind. All right, now let's apply alpha and beta to a formula. So what is that going to look like? We're going to have tan of 45 plus 30 equals sine of 45 plus 30 divided by cosine of 45 plus 30. Okay? Now applying the sum identities to the numerator for sine, we'll have sine 45 cosine 30. Notice the trig functions are different. Sine will stay the same plus cosine 45 sine 30. Okay? That's for the numerator. And then for the denominator, we are going to have um, cosine 45 cosine 30. Trig functions stay the same, sine flips, minus sine 45 sine 30. Okay? Now, what is sine 45? Let's do the numerator first, evaluate each expression in the numerator, and then we'll shift to the denominator, okay? All right, so what is sine 45? Sine 45 is the y-coordinate for 45 here, which is root 2 over 2. And then cosine 30 is the x-coordinate here, which is root 3 over 2, plus, what is cosine 45? The x-coordinate for alpha, which is root 2 over 2, times sine 30 is the y-coordinate here, which is 1/2. All right, let's shift to the denominator. What's cosine 45? Cosine 45 is the x-coordinate for 45, which is root 2 over 2. And then cosine 30 is the x-coordinate here, which is root 3 over 2. Minus sine 30, sine 45 is the y-coordinate for 45, root 2 over 2, times sine 30 is 1/2 right here. Okay? Okay, now we're going to multiply across the fractions. On the top, we have root 6 over 4 plus root 2 over 4 divided by root 6 over 4 in the denominator minus root 2 over 4. All right, you just multiply across numerator, numerator, denominator, and denominator. When I combine the fractions on top, I have root 6 plus root 2 over 4 divided by, in the denominator, I have root 6 minus root 2 over 4. Okay? Now, since I have a fraction in the numerator and the denominator, I'm going to multiply the numerator by the reciprocal of the denominator. Okay? So let's shift over here. So that's going to give me root 6 plus root 2 over 4 times, you reciprocate the denominator, you drop change flip, 4 over root 6 minus root 2. Okay? Now the 4's divide out, and we're left with root 6 plus root 2 divided by root 6 minus root 2. Now, we can have square roots in the denominator, so we have to rationalize this denominator. Since we have a difference of 2 radicals, we have to multiply by the conjugate, okay? So we have root 6. The conjugate is what you get when you flip the sign in the center. Since this is minus, you have make it a plus root 2 in the denominator and in the numerator. Okay, we're trying to create a difference of squares in the denominator, so the square roots cancel out. That's the whole idea of multiplying by the conjugate. All right, root 6 plus root 2. All right, so we're just going to fold this out first, outer, inner, last. There are other tricks that can be used here, but let's just do it the long way. So if we do that, in the numerator, root 6 times root 6 is root 36, multiplied radicands. Root 6 times root 2 is root 12. Okay, we've done first outer. Now inner, root 2 times root 6 is root 12. And root 2 times root 2 is root 4. Inner and then last. Okay, now let's shift our attention to the denominator. We're going to use the same procedure, first, outer, inner, last. So when we do the first, we're going to have root 6 times root 6 as root 36. And then that's the first. And then outer, root 6 times root 2 is going to be positive root 12. Inner, negative root 2 times root 6 is going to be minus root 12. And then last is root 2 times root 2 is going to be minus root 4. All right? So that's what you get when you distribute the denominator. Remember, there are other ways, shortcuts you can use, but I'm trying to do it the long way so everyone understands. Okay, let's go ahead and simplify this. This simplifies into, let's see, we have root 36 is 6, right? So 6 Root 12 plus root 12. Imagine that there's a 1 right here, okay? You have a 1 right here and a 1 right here. So if you add 1 root 12 and 1 root 12, what are you going to have? You're going to have 2 root 12, okay? 2 root 12, square root of 4 is 2 plus 2, divided by, and then in the denominator, the square root of 36 is 6. These two are opposites, so they add out to 0, and the square root of 4 is 2 minus 2, okay? So here we have 6 plus 2, add like terms, 6 and 2 are like terms, equals 8. Now let's see, how can we rewrite this? 2 root 12. What is root 12? Root 12 can be broken down 2 times 6, and then take out another 2, 2 times 3. So these two 2's are a repeated factor. If you take the square root, you're going to get 2. So you're going to have 2 on the outside because the square root of 2 times 2 is 2. And you're left with this 3, which cannot be rooted, so it stays as a radicand. So it's 2 root 3. But there was a 2 here before. So it's going to become plus the 2 that he had times this new 2 that came out of the root 12. 2 times 2, root 3. Okay? Over 6 minus 2 is 4. Okay, simplifying further, we're going to have 8 plus 4 root 3. And we can divide this denominator to both of them. Over 4 over 4. Simplifying further, we're going to have 8 over 4, which is 2. 4 over 4 is root 3. Okay? So what does this mean? This basically means that 75 degrees is 2 plus root 3. Okay? There you have it. Now this is method 1. Now let's go ahead and use a different method. Hopefully we get the same answer. They will have confidence that the result is correct. Okay? So method 2 actually involves the use of the sum identities for tan. Okay? We use the quotient identities as a substitution, but now we're going to use the sum identities for tan for real. All right? Okay, so what is the sum identities for tan? The sum identities for tan is tan alpha plus beta, and then you have tan 1 tan. Okay? So you have tan, 1, tan, and then let's go ahead and resolve the signs. So basically we know that the sign on the top is the same as the sign here, and the sign on the bottom is the opposite. Okay, so that goes the formula for the sum identities for tan. Okay, now alpha was established before to be 45 degrees, and using our unit circle, we know that the coordinates for that is root 2 over 2 and root 2 over 2. Okay, and then we knew that beta also is 30 degrees, which is root 3 over 2 and 1/2. Okay, now how do you find the tan of alpha and the tan of beta? That's the question. Um, we're going to use the unit circle ratios. Okay, so tan is y over x. Okay, let me write that properly. Tan theta is y over x. So that's the key. We're gonna divide our coordinates here. So this is x and this is y. So let's go ahead and look for tan 45 first, tan alpha. So tan 45 is going to be y over x. So it's going to be root 2 over 2 divided by, that's y, divided by root 2 over 2. Okay? So how do you divide two fractions? You multiply the first by the reciprocal of the second, right? So root 2 over 2 times 2 over root 2. This 2 divides out. And then root 2 divides out. And your final answer is 1. So tan 45 is 1. Okay? All right, beta. Tan 30 degrees. We're going to use the same idea, y over x. So for 30, this is y, this is x. So you have 1 over 2 divided by root 3 over 2. And then you multiply the first by the reciprocal of the second, or you drop, change, flip. So you drop this, change this to times, and flip that to 2 over root 3. The 2's divide out. Multiplying across, you're going to have 1 over root 3. Okay? You cannot have a square to the denominator, so we have to rationalize, right? So root 3 top and bottom, and then that's going to yield root 3 over 3. Okay, so that's tan theta. Okay, so we know what tan 30 degrees and tan 45 degrees are, so we're going to use them in our formula. So also applying alpha and beta in this formula right here, we're going to have the following expression: tan 75 degrees equals tan 45 plus 30. Now applying the some identities for tan, we'll have tan 45 plus tan 30 over 1 minus tan 45 tan 30. Okay? All right, now we know what each of these are, right? We already established that, found what they were up here. So tan 45 is 1, plus tan 30 is root 3 over 3, divided by 1 minus tan 45, which is 1 times root 3 over 2, or I'm sorry, over 3 for tan 30 degrees. Okay, so there you have it. Okay, now let's go ahead and simplify these. To simplify those, we just have to find the LCD, okay, and then we'll combine them. So we're going to have, let's move it over here, 1 over 1 plus root 3 over 3 divided by 1 over 1 minus root 3 over 3. So the LCD on the top is 3, so multiply this by 3 top and bottom, so the denominators are the same. Same story here, multiply by 3 top and bottom. So that yields 3 plus root 3 over 3 in the numerator divided by 3 minus root 3 over 3 in the denominator. Okay? So what you're going to do next is multiply the numerator by the reciprocal of the denominator because you're dividing two fractions. So we're going to have 3 plus root 3. You drop the top, change the division to times, drop change, and then you flip the bottom into 3 over 3 minus root 3. Okay? Now you notice that these 3's divide out. So when you multiply across, you are going to have 3 plus root 3 over 3 minus root 3. Now, we cannot have a square root in the denominator, so we need to eliminate the square root. But we have two expressions here, so we need to multiply by the conjugate of the denominator. Okay, so we have 3 plus root 3 in the denominator and 3 plus root 3 in the numerator. Okay, remember to find the conjugate, you just alter the center sign so we have a difference of squares. Okay. All right, so let's pull it out. In the numerator, first, outer, inner, last. First gives us 9. 3 times 3. Outer is 3 root 3. Outer is 3 root 3. And then inner is 3 root 3. And then last is root 3 times root 3, which is root 9. Okay? And then in the denominator, we'll do first 3 times 3, which is 9 first. And then outer is plus 3 root 3. Inner is minus 3 root 3. And then last is minus root 9. Okay, root 3 times root 3 is root 9. Okay, let's combine like terms on the top. On the top we have 9, but root 9 equals 3, right? So we can add 9 and 3. So that gives us 12. Or let me just show you the steps so you don't get confused. So we have 9 plus, and then combine these two. It gives us 6 root 3. And then root 9 is 3. All right? In the denominator, we have 9 plus. These two are opposite, so they add up to 0. And then the square root of 9 is 3. But this minus multiplied by a plus is going to make this a minus. So basically, what we have, if I want to show you the steps, is 9 plus 0 minus 3. Okay? All right, let's simplify further. We're going to have 9 plus 3 is 12. 12 plus 6 root 3 9 plus 0 minus 3 is 6. Okay? And then we can break it apart into 12 over 6 plus 6 root 3 over 6. And you notice they divide out and you end up with 2 plus root 3. Okay? And that's exactly what we got in the original method, in method number 1. So we're confident that our answer is in fact correct. Okay? So that goes to two different ways of evaluating sum or difference identities for tan. So thanks so much for taking the time to watch this video. You can feel free to subscribe to my channel by clicking up here. And if you like this video, you can click like down here. I appreciate it. And please, please, please post a comment. Tell me what you think. More clips can be found on mathgoodserve.com. Thanks again and have a wonderful day.